Although everyone would like their programs to run perfectly as soon as they're written, that's never really the case. And so, every programmer needs to come to terms with the fact that a lot of programming time will be spent dealing with errors. In fact, if you have the right attitude, tracking down bugs can be a detective-like challenge where you gradually follow clues to find the source. Now, we've talked about errors before, and we've seen one of the main tools for checking that a program is error-free: writing good test cases. Good test cases help make sure that the code is running as expected. If a program is giving the correct output for every input, and if the test cases are chosen well to include a few of the average or typical situations, but also check the edge cases, you can have a lot of confidence that your program is working. But what happens when we actually do encounter a problem? Say we've written some tests and run them, and now know that we have errors to fix. What do we do? How do we go about creating code that's entirely free of errors? Well, in this lecture, we're going to look at a systematic approach to debugging. We'll also look at how C++ uses exceptions to deal with a large group of errors that happen at runtime. Now, often when I'm teaching new programmers, and even when I'm teaching people with enough experience that they should know a lot better, I'll see people wildly flailing around, making guesses as to what might be the problem, and changing sections of the code that they didn't understand as well, hoping that some random perturbation of the code will make it work. And this is a recipe for frustration and failure. Instead, the idea is to approach the process of debugging methodically. I like to think of debugging as following 6 main steps. First, isolating the error. Then, narrowing in on the failure point. Identifying the problem. Fixing the problem. Retesting. And finally, considering similar cases where the error you fixed might reappear elsewhere in your program. In fact, if you learn nothing else about debugging, know this: debugging is a methodical process. It's not just a matter of randomly jumping through your code to find errors and make bugs disappear. So, let's discuss this entire process of debugging, where the steps are isolate, narrow, identify, fix, retest, and look for similar cases. The first step is to isolate an error. This is where the test cases that we came up with before come into play. We want to run tests until we can either not find any tests that give problems, or we find a test that gives a repeatable error. Now, it's important for the error to be repeatable. We want to make sure that every time we run the program with that test, we get the same incorrect result. Now that we have functions, a common version of the test case is to set up what's called a unit test. A unit test is a test case that's run for a particular function. Basically, we have some input to the function, and then we have some output that we should expect to see. When we write a function, it's a good idea to run several unit tests to make sure that the function is working as expected. So, let's look at a sample unit test for a function. We have here a program that's designed to let a user enter some text, and then it will check whether that text is a palindrome or not. It does this by calling a function isPalindrome. That function calls a function removeSpaces to remove spaces from the text. Then it goes over the first half of the characters, comparing them to the corresponding character on the other side. If they all match, then it's a palindrome. Otherwise, it's not. Since we're focused on the isPalindrome function, we can consider this a unit test of the isPalindrome function itself. We want to give the isPalindrome function an input and check that it's giving the right output. So, for our unit test, we'll check to see if our function works for a very simple text string, AAA. Now, that should be a palindrome. But when we run the program to check it, we get the wrong answer. So, we've accomplished step 1 of our debugging process. We have an error that we can use to debug our program. The next step is to hone in on where the failure is occurring in the code. This is where the debugger in Visual Studio on a PC or Xcode on a Mac can come in very handy. A debugger can only help you follow what's going on in the program. It's not going to solve your issues for you or even tell you where the error occurred. Your goal is to find the first line of the program that gives a result that's clearly incorrect. Usually, this will mean that some variable in memory has the wrong value. Now, if you don't have a debugger, you can always use the poor man's debugger, output statements. And there are many, many times when I've debugged a program not by using an IDE's debugger, but rather printing out data along the way. So to hone in on an error, you should start at a point in the program where you know that everything is okay, and one where you know that things have gone wrong. In the worst case, that'll be the first and last lines of the program. But in many cases, you have a better idea, often right before calling some new function you wrote and right after it. And then you'll want to gradually narrow down the scope of the program where the error could be occurring. Pick another point in the program, somewhere between the last known OK point and the first known bad point, and then analyze whether the variables in memory are correct at that point in the middle. If everything looks good, then you can move your OK point to there. Or if there's a problem at that point, then you move your bad point back up to there. The goal is to narrow down the location of the error, where things first go wrong as much as possible. Okay, let's see what it looks like to hone in on our error. We know that things are good at the beginning of the program, and we know there's a problem at the end. So let's check a point in the middle. To illustrate how we could do this with just print statements, I'm showing a print debug approach this time. I've inserted one line after the remove spaces function has returned to output the result there. Running the program, it appears that the data is correct to that point. That indicates that we did indeed read in the string, and calling remove spaces did not introduce any obvious errors. So we can assume that up until that point, things are good. Now we could likewise check the value that we're going to return right before returning. If I add another output line there, printing out the value that will return right before the return statement, we can check if the problem is before or after the return line from the isPalindrome function. Sure enough, when we run the program, it's returning 0 or false, which is not correct. So we know that things seem good before the for loop, and they're wrong after. We need to hone in farther. I'll switch now to showing what this looks like in a debugger. We can set a breakpoint at the beginning of the loop. That'll make sure that we stop there. We run the debugger to that point. Looking at variables, could be palindrome is true, as it should be. Stepping over the first line, we can check and we see that I has the value 0, just like we'd expect. So things seem good so far. Stepping over one more line, we've ended up inside the if statement, and are about to set could be palindrome to false. Wait a minute, that's not right. We should not be getting to this point for this input. So that means that the error had to be on the previous line, the one where we're comparing no spaces sub I with no spaces sub no spaces dot size minus I. We can examine those values. I is 0, like we'd expect, and no spaces dot size minus I is 3. Wait, that's not right. We want to be looking at the last element of the string, but that should be element 2, not element 3. Now on to our next step. Since we know where the error is occurring, the third step is to identify the source of the error. Now, the source of the error is not just the line of code where things went wrong. The source is what caused that line of code to be wrong. Was it a simple typo? Did we forget about a particular edge case? Or is it an error in the fundamental logic of the program? The key point here is that we want to understand what caused this error before we try to fix it. If it was a basic error like mistyping, then it'll be very simple to fix. But if it's a logic error in the program, we want to make sure that we really understand what went wrong and why. Now there's no shortcut around this part of the debugging process. You've got to use your brain. The key idea here is to understand the why of the error, and not just the what and how. In our palindrome program, remember that for a string of 3 characters, we were trying to compare character 0 to character 3. And if we think about it, we'll realize that I made a mistake when writing the formula. I incorrectly thought the last character would start at the size of the string, but it's actually the size minus 1. So I need to compare character 0 to character 2. So in this case, my error was in coming up with the wrong formula to use for comparison. So our next step, now that we know the problem, is to fix the bug. This could be simple, maybe just spelling a variable name correctly, or changing a character. It could involve rewriting a line of code. Or it could be that you were so totally wrong in your approach that the best fix is to throw the whole thing out and start over again. And I'm not joking either. I've seen many times where people spend long hours of effort trying to fix bad code, where if they had just thrown it away and written new code from scratch, they probably would have gotten error-free code in a small fraction of the time. Here's the fix for this bug, and it's pretty simple. I just subtract 1 from the element number for the end of the string. So, when I is 0, then I should be comparing to size minus 1. When I is 1, I'll be comparing to size minus 2, and so on. Then, once an error is fixed, you need to retest everything. Your goal is not just to show that the fix you made fixed the one problem that you'd isolated and identified. You want to make sure that you didn't break anything else in the meantime. If you've saved all of your tests, now's the time to rerun them and make sure you still get correct results for everything that was previously correct, plus for the test that you just fixed. So, back to our palindrome program, we now want to test it. Sure enough, when we test it on AAA now, it returns that it is a palindrome. And we could check other tests like ABC is not a palindrome. BOB is a palindrome. And so is a man, a plan, a canal, Panama. It seems to be working now. Finally, before our debugging task is done, there's one more step. We should stop for a minute and think about whether anywhere else in the code is likely to have a similar error. It's like finding a brake problem on one wheel in your car. If one brake pad is worn out, chances are at least one more is as well. Errors tend to multiply when there are different versions of the same calculation. Sometimes people copy and paste code from one area to another and thereby duplicate any errors. Other times, if your thought process was off, you might have made the same conceptual error in other parts of the code. The key here is to spend time thinking about whether the fix you made would apply somewhere else as well. If so, fix and test that other part of your code as well. So for the palindrome program, we should think, were there any other places where I was assuming the string went all the way to size rather than to size minus 1? In this case, the answer is no, so we're done debugging. Now, the errors that we encounter tend to fall into one of three types: syntax errors, logic errors, and runtime errors. The first of these is the syntax error, where we've written something that's not accurate code. These are usually the easiest to find and fix, since the compiler will identify that you have a mistake in your code and usually give you a particular line of code where it detected the error. The second type of error is the logic error, like the palindrome example from earlier. This is where there was something wrong with the thought process that went into the code, and that gets reflected in a mistake. These are some of the toughest errors to find. The third type of error is a runtime error, due to unexpected circumstances. And this is where adding something called exceptions to your program can be a big help. Often, the source of the error could be due to circumstances outside the programmer's direct control. Perhaps you asked a user to enter the number of boxes, and they typed a word instead of a number. The program will either give you a wrong answer or just crash. Now, to avoid this kind of error, you could make a much more complicated process for reading in a string, then checking to see if the string is a positive integer, and if so, convert it to an integer, and so on. But doing all of this would be very painful. Programming is full of situations, besides a user entering data of the wrong type, where we might run into results that we don't expect. One common situation is with files. We might try to open a file for reading, but the file just isn't there. Maybe the name got mistyped, or the file is in a different directory. For whatever reason, it's not where we expected, and we can't open it. If we try to run this code, we'll probably get some sort of nonsense printed out. I misspelled the name of the file, so what is supposedly input from the file is junk. Trying to access a vector is another situation where what we expect might not be what we get. For example, maybe you read in a week's data, but a user included only the work week and not the weekend. What should happen if you try to access the 6th element? The code here is an example. The hours worked vector has 5 elements, giving the number of hours worked each day. The loop, however, tries to access 7 elements. The solution to dealing with unexpected, exceptional cases is through the use of exceptions. Here's how they work. First, we have a function called from somewhere within a program. This call should occur within what's called a try block. Somewhere within the function that's called, we encounter an error. This is where we realize that some exceptional situation has occurred. Maybe we've tried to access past the end of a vector, or we had text entered instead of a number. That function then generates what's called an exception. And this is basically a special note that something's gone wrong. The term we use in C++ is that we're going to throw an exception. In other programming languages, you might hear this idea called raising an exception. When we throw an exception, the function immediately returns. The exception is being thrown back to the function that called the routine. Now, back in the calling function, the exception is then caught. There's a separate code that's executed to handle the exception that occurred. So let's first look at how we could catch some exceptions in our code, and then we'll look at how to throw exceptions ourselves. If we're going to deal with exceptions, we need 2 parts of code. First, we have a try block. The try block consists of the word try, followed by curly braces. Now, whatever code is inside of the curly braces is something that we will try to execute. If the code executes and no exception is thrown within that code, then we go on to whatever additional code follows. On the other hand, there could have been an exception raised. Immediately following the try block will be 1 or more catch blocks. A catch block is used to catch any exception thrown when trying to execute the code in the try block, including in any functions that were called from there. The catch block will take a parameter, which is going to be the exception that's returned. We'll see a little bit more about that parameter later. Now, in most cases, we're going to be throwing our own exceptions, but there are a few places in standard C++ where exceptions are already thrown. So let's return to the 2 examples we saw before and see how we'd handle exceptions in those cases. Remember the situation where we tried to read from a non-existent file? Well, the fstream library actually supports the ability to throw an exception in a case like this. There's a special command that has to be run for the fstream first. This is the member function exceptions, and it basically activates the ability for fstreams to throw exceptions. The exceptions function takes in as input the exceptions that are being activated. So in this case, the exception that we would care about is a predefined exception called failBit. If the file does not open correctly, then a failBit exception is thrown. So for this code, since the fstream is named infile, and the command that we'll write is infile.exceptions, open parenthesis, fstream, : failBit, close parenthesis. Then we have a try block, where the code that we want to try to run is put inside the curly braces. In this case, the code that we're trying is opening the file. Following that is a catch block. The catch block takes in 1 parameter. The parameter is a reference to an exception, and I give it the name category in this case. Inside of the catch block is the code that we want to run if the exception is caught. In this case, we print out a message that there was an error opening the file. Then we return a non-zero value. Since we're in the main function, return means that the program ends, and since it ended with a non-zero value, it indicates that there was an error along the way. If we run this code and the file does not exist, then the open function that we tried to call will generate an exception. And when this exception is caught, we print out error opening file and the program ends. If there was not an exception, then we would have just skipped over the catch block and gone on to the remaining code in the main function. Okay, so that's how we can use try-catch blocks. What about when we're writing our own programs? How do we actually throw an exception ourselves? This turns out to be really simple. We just call the throw command. We need to throw exceptions, so the syntax will be throw exception parentheses. That creates an exception and it throws it back to the original function. So here you see a piece of code that might be used in the situation we began discussing. Imagine we have some function named processBoxes that takes in an integer parameter. It makes no sense if that function is called with no boxes, so in that case we might want to throw an exception. Inside the function we perform a check. If the number of boxes is less than 1, then we have an invalid input, and we'll throw an exception. To throw the exception, we just have throw exception parentheses. An alternative is that we could create an exception variable, exception bad input. Then we could throw that exception, throw bad input. Either way, what's happening is that we're creating an exception and then throwing it. In most circumstances, it's easier to just throw the exception in one line of code that both creates the exception and throws it. But there are ways to add additional detail to the exception, and when people do that, they'll sometimes want to create the exception, add whatever they want to it, and then throw it. Now, if we didn't throw an exception, then the function would continue to do whatever else it needed to. Back in our calling function, we can try calling the routine with an invalid parameter and catch the exception being thrown back, which results in printing a message that there was an exception. One other thing to note. Here we had to pound include standard except, std except. We didn't do this in our earlier examples since including vector or fstream automatically included basic exceptions as well. But if we don't use another library that's using exceptions already, we need to pound include it ourselves. We'll see how to do even more with exceptions, including creating a lot of different types of exceptions when we get to object-oriented programming in a later lecture. For now, though, realize that there could be different types of exceptions. These can be thought of as specialized versions of the more general idea of an exception. Rather than just exception, there are specific exception types named logic error, runtime error, range error, and so forth. We can have separate catch blocks for each of the different types of exceptions. To do that, we just define the parameter in parentheses after catch as having the more specific type of exception, rather than just the general term exception. So, here's how we could modify the earlier example of reading past the end of a vector to catch different types of exceptions. Notice first that we again have to pound include std except. While vector allows for plain exceptions, it doesn't include logic error and runtime error. In our calling routine, we now have two catch blocks. The first one handles runtime errors, and the second one handles logic errors. Each of them prints a different error message. When we run this code, we see that we get the encountered a logic error message when we try to access outside of the vector itself. There are a couple more notes I want to make. Let's look at one more version of the vector past end of range case that we saw earlier. I've made some changes here to each of the catch blocks. First, the parameter that's taken into the try block sometimes has more information about what the exact error is. This information is stored in a string, and it's accessed using the what command that is part of the exception. In the example, each of the catch blocks is now printing out the what function of the exception. cout stream except dot what parentheses stream endl. So it should print out a little detail about what the exception was, if it's available. Second, when we encounter an exception, after catching it and doing something at that stage, we need to go ahead and notify the previously called function that there was an exception. Notice in the example that each catch statement then throws an exception again. So if this code were in a function besides main, then the function that called it could go ahead and catch the exception also. And that sort of propagates the exception on up the set of function calls until either the program ends or we reach a point where the fact that there's an exception can be dealt with. Now, when we run this and we encounter our first exception, we get an output that gives a description of exactly what the exception is. Also, notice that we now only get one error message. That's because as soon as we encountered this first exception, we threw another exception from the catch statement, thus ending the main function call right there. One other point to note is that we can throw exceptions of more specific types. And if we initialize the exception with a string, then this string can be obtained by the catch statement using the what command on the returned exception. Let's look at one final example that puts all of this together before moving on. We'll create a function named findResult that basically just returns the square of an integer, but will return exceptions in some cases. In the event that the input parameter is negative, we'll return a logic error containing the message negative argument. Notice that we're throwing a logic error, and that in the parentheses used to initialize the logic error, we put the string that we want to return. Also, in the event that the input integer is greater than 10, we'll return a runtime error, this time with the message argument too large. Notice that in this case I created the runtime error, initializing it with the string, and then threw it. Now, back in the main function, we have an infinite loop. And in the loop, we're going to try to read in an integer from the user and then output the result of calling the routine. We have two catch blocks, one for logic errors and one for runtime errors. Both of them are nearly the same, outputting either logic error or runtime error, and then the what result from the exception. So when we run this code, we see that giving a number like 3 does indeed print the square of the number. That is, the program got the number 3, called the routine, and it just returned as expected. Entering the number -1 generated a logic error exception. This was indeed caught by the logic error catch block, and it printed out the what result, which was the message negative argument, just like we created. Likewise, entering the number 30 generated a runtime error exception. Again, this was caught by the runtime error catch block, which printed out the message argument too large, using the what function on the exception. Using exceptions can help make our code much more robust. That is, our code is able to deal with a wider range of exceptional circumstances cleanly. Now, exactly how we deal with those circumstances can vary. We could just close the program, maybe after printing some error messages. We could prompt the user for another input if the source of the problem was user error. We could just set a default value that gets used if a value given to us is invalid. Exactly how we handle exceptions is going to be really case-specific. Now, debugging is not always very easy, and it can be a challenge. There are people in the software industry whose sole job is to help find and deal with errors. But it can be quite satisfying to track down bugs and clean up your code as the bugs are removed. Remember that you've got lots of tools to help you, from ways to design tests, to using a debugger, to the use of exceptions to catch errors during execution. The main thing I'd emphasize, though, is to treat debugging as a methodical process. Isolate with test cases, narrow them down with the debugger, identify whether the error is a syntax error you can retype, an unexpected case you can handle with exceptions, or a logic error that needs a bigger rewrite. Then, after you understand the problem, fix the error, retest everything, and look for similar cases elsewhere in your program. Don't just go flailing about, changing things willy-nilly. If you approach debugging steadily and systematically, you will find your errors.